So there are two things. So first of all, one student just come to me that some of you could not be here today because of the typhoon. So I just set up online Zoom link and just post a Blackboard. If any of your friend could not be here, just send a Zoom link to him or her. Okay, this is the first thing. The second thing is I received several emails from you and waiting to apply the research assistant position or doing research in my group. So one thing is, so one chance is that you can join the dissertation. Some of you have the dissertation, right? Do you have? That is one chance that you can join the research program. And the other thing is we do not admit part-time research assistant position. So only after this semester or after you graduate, you can apply. Okay? So because I received too many emails, I could not reply each of you, many emails, not only from you, also because it's application time for next year PhD. I received several emails. So I could not just reply one by one. Sorry about that. Okay? So how was your day today? This morning? What about your lecture for this morning? Are they canceled or just moved to other times? Canceled. Okay. And so today we will continue our lecture, Computing 5511, Artificial Intelligence Concepts. Remember what we covered last week. Basically, we cover the history of AI from three components. What are they? Remember? What are the three components? Consist of the entire history of AI. Forget about it? We talk about symbolic AI. Basically rule on logic and neural AI, this neural network part. And what's the last part? The one basically is not AI, but the component, mass, foundation, predicted AI. What is that part? Statistical AI, right? Remember that. And we also clarify what's the difference between artificial intelligence, deep learning, machine learning. What's the difference? What are differences between these three different concepts? Remember, this course, they are found down to the ideas, the concepts. What is artificial intelligence? What is deep learning? What is machine learning? What's that? So basically, artificial intelligence can include all machine learning. Machine learning, one part of machine learning, that is deep learning. Except deep learning, we also have linear regression, linear classification, right? So on and so forth. These are not deep neural networks. So we call that one part of machine learning, but not deep learning. Okay? Okay? And basically, why AI is so powerful? We mentioned two main drivers. What are they? Compute and data. So that's why it is so powerful today. Okay? Okay? Okay. So any of you heard about agent? Play with agent these days. In fact, these days, there is a term very popular, multi-agent system that can make everything autonomous. So what is agent basically? something that can act, make decision rationally, that we think that it can do, and how it can perform these kind of behaviors. That basically related to lots of search algorithm. That's why for today, we are going to talk about searching. So let's take a look at this map. So right now, we are at Hong Kong Polytechnic University. Suppose you are going to go K11. This is K11. This is a very luxury shopping mall. So we are in here. How do we get in here? You can either walk along the harbor. Then you can see a very pretty scene. You also can take the bus, or you can take the subway. There are different ways. You can go from one source to the destination, right? So this basically is a searching task, and you have different objectives. Either the cheapest one, shortest one, and the one that takes your less time, or you can buy more things you want. These are different objects, and you can take different actions by using different ways. For example, you are walking there. Turn left, turn right, go straight. This is our action space. This is one particular example. So what about the Google Map? Anything that you can think of, it is related to AI. My PowerPoint is not, okay, it works sometimes. So any function you think it is related to AI. This is something that you use possibly every day. Not only Google Maps, like Tencent, the Baidu, right? The Google Maps, what the function that you think it is related to AI? Anything? So silent? Last week, I encountered a student in this room, and we just chat a little bit. Still, because you think it is, you are so, oh, you're so silent. Okay? Don't think that your English is not good. That is if you are keeping not practice, of course. So what's a function you think it is related to AI? Recommendation. If you search Google, you can see, you can search, it can recommend you restaurants. The surrounding things you can take a look at. This is personalization, one thing, right? And that also, if you want to search one destination to another, it can recommend you different paths. And also it can tell you how long you can take it to there. There are something that can predict traffics. That is traffic prediction. So how do I model these maps and give you so many different recommendations? This is something you can use AI, recommendation system, right? And if you take a look at the map, you are searching one to the other. Given this entire map, you can model it as a graph. You can model the road intersection as nodes and the interaction as nodes and the road segmentation as edge. Then you can search one to the another. Then this will relate to graph theory. And we'll talk about the different searching algorithms with this graph modeling. Okay? So this is one particular applications that we will use searching algorithm. So what about the next game? So have you played with Rubik cube? Is it easy to you or difficult to you? Basically, you just load the cube, right? To make one configuration to another. Or you can play with this 15 puzzle. You can move the cube, the number of cube, up, down, left, right, to from the left configuration to the right configuration. So there are actions in here, move up to right, rotate one piece of cube or another. So what's our objective? We are going to move this one configuration to another configuration with minimum of time. This can be one of your objective. And these are set actions you can make. We say you have this action space, you are going to search. The objective is you're going to minimize the number of actions. Also, you can say that you want to minimize number of time you play with these games. Okay, these are one of the other applications. And the robot, we showed you the robot last week. Robot manipulation. Basically, we are going to move the robot from one post to another. These are also one control. But they can also have different actions, accelerate or throttle, right? Throttle. And so this is the first robot that developed in 1966 to 1972. The algorithm that used is A-star algorithm. So like today, what we are going to introduce, they are not modern AI, but still many industry still using it. Like A-star algorithm, we are going to introduce today. Google Maps still use this algorithm for searching the destinations. Okay? Okay? So have you imagined that one day, one robot just sit at your kitchen and help you to cook your food, prepare your food? This is the future. Robots can replace the labors for us, can make food for us. So let me show you a recent research that they make a robot that can make dumplings for you. Okay, we have around 6 students. Okay, I haven't admit them. Give me 1 second. Hello? Hi. So can you hear me clearly in here? Okay, cool. Because of bad weather? Okay. So make sure all of you can hear me clearly, all right? So right now I'm going to show recent research that make robots to make dumplings, okay? But still, that's something that under research, not so mature yet. So online, guys, can you see the web page in here? Okay, yes. And right now I'm going to show you a very short video showing a robot can make dumplings for you.
too thick for a roll, it will likely stick to it. As perhaps the most critical step in something, robot fit over perfect flatness of thickness. The dough must have the perfect thickness for something like that. The robot uses a circle cutter to cut a circular dumpling skin out of the thin dough. The robot then uses a pusher to push away the excess dough. Now we have the dumpling skin ready, but we still need to move the dumpling skin to the dumpling mold. Here is where the skin fashion will come. The robot uses it to pick and place the dumpling skin onto the dumpling mold without deforming the shape of it. Then the robot selects the filling spatula to pick and place the dumpling filling onto the center of the dumpling skin. Finally, the robot uses a hook to hook the handle of the dumpling to close, press, and open to finish the dumpling making pipeline. This video shows that dumpling making is a highly long horizon and challenging task. Even a single error made during the decision-making process might break the entire pipeline, but our method can reliably accomplish this task. The task of making alphabet letter cookies is to manipulate a piece of square dough into the shape of alphabet letters with all the available tools. Here's the video of making R, O, B, C, and K to compose the word robot. For the letter R, the robot uses the two-rod symmetric gripper to pinch the cavities in the R, and uses the circle punch to create the hole. Both these actions require high precision to make a good-looking R. For the letter O, the tool classifier predicts that the two-plane symmetric gripper is the most appropriate tool to pinch the square into a circular shape, and that the circle punch should be used for the hole in the O. The robot presses twice with the punch to make the hole in the O more defined. For the letter P, our method recognizes the asymmetry and identifies the asymmetric gripper as the suitable tool to accomplish the task. Next, the learned policy finds the accurate locations for the circle punch to press by comparing the current state with the target state. The letter C is a more challenging part since the distance between the initial square and the target curved shape is large. Our method successfully plans the cooking position on the fly based on the closed-loop visual feedback to shape the food. For the letter K, robot uses a combination of two rod symmetric that on the top, right, and bottom side of K.
Okay, if you take a look at this video, what do you see? They use a robot, so you need to control a robot and what anything else from the action. What's the feedback from? Do you look at it very clearly? What's the feedback from? When it shape the shape it want. You can see the move that different times, but when to stop? What's that? How does a robot know? That you the one to make the to a C to a K later. How does it know? What's that? Huh? What's that? Exactly. So there's a vision feedback. So one thing, there's a camera to look at the shape if that is match the target state. Otherwise, they continue to shape Okay, so this is one thing. And right, and I also use the video as the demonstration to control robots. So this right now is a very hot research topics in these days. And if you look at the robot in 1960, 1980, the first one, basically they set off predefined rules. That is not so intelligent at all. They have predefined states, and they use the searching algorithm to search over and then to the target objectives. But in this case, people are trying to make robots intelligent by using the demonstration or use video or this camera information to control the robots, to make the decisions, okay? This is the intelligence we're going to make, and this is the future, all right? And so any of you think that might have problem here? Let me show you a failure model. And that's it. If just stick it over there, it could not do anything. So there's lots of different accident would happen. Okay, this is the failure mode, one of the case. Okay, since here, what we're going to say is the searching algorithm. This is the second component that we're going to cover. Okay, and for this week, so what is searching? What is searching? It is the process of looking for the solution of a problem through a set of states. We have several states, different states, like playing the games. Which configuration, a particular configuration is a state. And conditions like current state, what's the current configuration? The step where the agent begins the search, and the goal, the target, what state we're going to reach, right? And what the action space. If you are playing the puzzle, then you can move a particular cube in left, right, and up and down. These are different actions you can perform. And you can move one configuration to another. So this in here we have the action. And then what is the cost? This cost can be time, can be energy, right? We can be the efficiency, the cost, what is cost, can be storage, anything you can define, anything objective you are going to minimize or maximize. This is the cost. You can take that as your optimization goal. Okay? Okay? So basically you can figure out a set of sequence so as to you can move one initial configuration to the target configuration while optimize your objective. This is what the searching going to do. Okay? Okay? And there are several properties. One is completeness. Whatever you have any input, they'll give you output. This is a completeness. And optimality. Even solution for an algorithm is guaranteed to be the best solution among all others. Then we say it is an optimal one. And time complexity. What do we say is computation efficiency and space. If you have taken the data structure algorithm, that will be the complexity analysis in terms of the computational resource and the storage, right? These are complexity. Of course, for this semester, we will not go into the detailed analysis. These are some basic characteristics that one researcher, they are designing such algorithms, what they will consider. If you look at the papers, last week we covered how to find the papers. If you are interested into a specific topic, you can take a look at papers. Usually they would have this kind of detailed analysis from different aspects. Okay? And so for almost every AI program, it depends on such procedure to find a solution. Not only the searching algorithm we are going to cover today, also like the deep learning. When you design a deep learning model, you have a model. That model will have a lot of parameters to train, to learn, to optimize. But how do we figure out the best parameters to make the model have a good performance? This is also an optimization problem, something that you're going to search a best possible solution, best possible model that can give you the best performance. The basic idea, they are the same, but they use different ways. Okay. So in this week, what we're going to cover is the one same category that whenever we have a current state, we are going to determine that is our target or no. If that is no, we are continue to move the action, to perform the action. As long as we move an action, we can judge if this configuration, if this state is what we want. Otherwise, we will move next. So basically, this process is repeated until the solution is found or the state space is exhausted. We just search over the entire space and we could not find out the solution. This one or the other. Okay, this is the entire abstraction of this type of searching algorithms. Okay. And remember, when we talk about the mapping, the map in there, before we get into the searching algorithm, we have to model the problem first. What is the states? Okay, what is the states? And usually we will define each state is a node. And the edge is a transition from one state to another. This is a data structure we are going to perform over and to decide which algorithm to figure out the target solution. Okay, usually that is based on a tree or graph. This is a basic data structure. Let me show you the game first. Tic-tac-toe. Have you played this game before? What's that? Tic-tac-toe. In fact, this is the first project when I was a TA at the University of Toronto. When that course is a C program. The first project is to design a C program that can play this tic-tac-toe game. So what's tic-tac-toe? I think there's a Chinese version called 连连看. Something similar to that game. So basically, there are three different options. One is just empty. This is an empty 9. For example, this is a 9 grid, 9 position. We have 2 players. And one player can represent the cross side. And the other side is the nut. So as long as you encounter either this cross or horizontal or the vertical line, 3 consecutive ones, then you win. This is a tic-tac-toe game. Tic-tac-toe game. Okay. And so as human being, we know how to play with it, right? We know one by one. For example, you can also play with a computer. There's one that Okay, if you are the player, one of the player, then there's a computer, the other side, right? So this is a game. Then this is a tie. This is a tie. So you can either two players, that's human, but how to design this computer program? What's the magic in here? What's the magic in here? If right now I'm asking you to design a program that can play tic-tac-toe, how do you do that? How do you do that? So if you look at this nine space grid, how many possibilities? You can just analyze. If you put just one, okay, got the time. Just if you put one as a player into 1 over this 9 grid, then will be how many possible response? Of course, 8. And then after you put the second one, the other side, right now, how many possibility you have? 7. So the possibility is 9 factorial. Space, that is an action space. And in each one, that is a state. Let me show you what the tree looks like. This is the initial state, empty one. At the beginning, we have 9 different options in here, right? And either the first position, second, the third, so on and so forth. There are 9 possibilities in here. Once you put in a particular position, then you have the rest 8 response possible. 1, 2, 3, 4, 5 possible solution here. 1, 2, 3, 4, 5, 6, 7, 8. So on and so forth. So in here, you can enumerate all of the possibilities in here. This is the problem formulation with a tree structure, given this tic-tac-toe game. And with this tree structure, right now, you can design a path that can you go from in this side to the root, to the leaf. One path that get you win or toy or tie, right? So this is what are we going to do? Given this tree structure, we need to design ascension algorithms to help us figure out a path, shortest path. How many of you have taken data structure algorithm, the course? 1, 2, 3, 4? Just a few? No way. I did this course in my undergraduate, data structure and algorithm, and we're doing lots of tree structure, tree searching algorithm. No? How many of you haven't taken data structure and algorithm this course? Didn't. Okay. How many of you heard about the shortest path tree? Shortest path. 1, 2, 3. Just a few of you. How come? Okay, so this is the first of all, if we want to play a game, you can formulate this game into this kind of graph or tree structure. with this kind of structure, there are a bunch of different searching algorithms you can use. That's on the shelf algorithm you can use. Okay, okay. So basically, these are a bunch of different searching algorithms can bring you to one to another to give you a solution. One type of search that is called uninformed search. As the name implied, we don't have any information except on the problem itself. We also call it blind search. There are two algorithms we are going to introduce today: breadth first search and depth first search. And the other type is informed search. That includes hill climbing, breadth first search, A-star algorithm search. This A-star algorithm search is the very, very popular one. Even this Google Map, they still use this A-star algorithm search in their Google Map search, okay, engine. And simulate annealing genetic algorithm. These two we are going to cover next week. So the uninformed search means that, as this name implies, we don't have actual information. We just have the initial state of the problem, the search operator, and the test for a solution. A test for if the solution is what we want or no. If that the solution satisfies our goal. Okay? Okay? Usually we just generate the successors and distinguish that state is the goal state or no. If that is not the goal state, we just continue to generate a new successor. This is the basic idea of uninformed search. Okay? Okay? And so generate a possible state and determine if that is the one. If no, just continue. Very, very simple idea. Okay? This is a very, very intuitive one. Okay. So breadth first search, is that the one you should familiar with? Something that I learned in the data structure and algorithm when I did my undergraduate. Basically, that is breadth first search, breadth, layer by layer, to scan the tree layer by layer and search if the state is what we want or no. Okay? If that is yes, we stop. Otherwise, just expand. All the nodes, layer by layer. This is the basic idea of breadth first search. Each node is a state. Each edge is a transition from one state to another. Okay? And usually we will use two lists to maintain and to design the algorithm. One is the open list. Open means a list of states that have been generated but whose children have not been examined. The closed list means that this list of states have already visited. Let's take a look at pseudo algorithm. Breadth first search, layer by layer. Okay, layer by layer. And this is initial state. This is the goal state. You just search layer by layer to figure out which one is going to next. Okay, okay. So what thing you are going to look at is how to use this to maintain list to figure out which one is your target state. We have the open list, two lists to maintain. The open list to maintain the one can generate a successor but haven't visited yet. The closed list is the one that we have examined, and it is not our target one. We just put in a closed list. Okay, okay. And so we just doing, this is the how we get to the ultimate goal. This is a procedure of this breadth first search algorithm, how to implement this scan layer by layer. At the beginning, we just remove the leftmost state from the open list to check one by one. If that is a goal, we just stop. Otherwise, if that is no, we just continue to generate the next one we are going to scan, we are going to visit. This is the children node of the X. This is the left node most. Okay? And we check if, because this have been checked, we just put in the closed list. Otherwise, the children list will be put in the right end of the open list. We can continue to check from the open list. Is that clear to you? Is that clear to you? Basically, we have two lists to maintain if a given tree. And we just, later on we have a toy example to illustrate how to perform this procedure so as to figure out the solution. Okay? What you're going to remember is that to remove the leftmost state from the open list, to check the leftmost one, and use the leftmost one to generate the successor. And this successor will be put in the right end. If we didn't find the target one, just put the right of the open. If that had been checked, we just put in the closed list. There's 3 pieces of information you're going to remember so as to you can look at the example. Okay, so given a tree, we have a bunch of nodes. Each node is a state, and you can change it from A state to B state, or from B state to E and F, so on and so forth. Right now, you are going to figure out a shortest path from A to something leaf node in here. Right now, we're going to do your breadth search to search the solution. This is the toy illustration of how this student example perform. We have 2 lists. One is open list, the other is closed list. This open list is going to maintain the state in here. We're starting from A, right? We're starting from A. We put A in the open list. And we're going to expand A in here. What are A's children node? They are B, C, and D, right? We check because A is not our target node. Then we are going to continue to put this children node into the open list. Because A is not, so we just put A in the closed list. Okay? Okay? And then we check from the leftmost of the open list, left B or D, leftmost, B or D. B or D. B, right? So check the leftmost of the open list starting from B. So B, we check because B is not our target. It's not our goal. So we just put B in the closed list, right? And we just continue to generate a successor from B, E and F in here. And we put E and F to the rightmost of the open list, E and F, rightmost in here. Right? And then we're going to continue check, because B is not our goal. We're going to continue check leftmost of the open list. That is C, right? So we're going to check from C. C is here. Expand C. Still, we check C is not our goal. We just generate the children from C, G and H. G and H is the next successor we're going to check. But we put them into the rightmost of the open list, rightmost, G and H in here. Right? You can see this process is iteratively. Is that clear to you? If you look at this toy example, it'll be easier to understand how to maintain this open list and the closed list from an initial state to the target state. Okay, if we look into the 6th step to check expand E, this is the 6th step. This A, B, E, C, D, they are all be checked. So they are right on the closed list. And these are something we're going to continue. You can see the check layer by layer. layer by layer. That's why it is called breadth first search. This is the order of being checked nodes. Okay, so why that is called a layer by layer breadth first search. Okay, so okay, in here we have the example. We have the initial state. We have the target state. This is our goal state. How do we use breadth first search to solve this puzzle problem? Let's take 5 minutes break and come back to give me a solution. Okay? Online, you can just speak out. Otherwise, I didn't know you say something there. Dongyun, right? Chenxi. You can just speak out if you're online. If you just text, I could not see what information you are going to convey. So far so good for you guys. I know it's a recording. Yes, I know. Hello? Yes. So any ideas? Tian Xiong, right? Do you have any idea? The guy online. So given this puzzle problem, and we have initial state and goal state, what we can do with this puzzle? Yeah, of course. In fact, A star is also one solution as well. Breakfast search, yes. But before that, we will have to present this as a tree structure, right? We will need to identify states and the tree structure first. So take a look at this add puzzle. We have the initial state. These are of initial configuration, right? And the action is to move a particular cube left, right, or up and down, but they have constraints. For example, in here, we only have 3 options. Either 7 left from left to right, or 6 from up to down, or move the 5 from move left, right? So we only have 3 options from the initial state to next state. And for the next state, of course, you can enumerate all of the possibilities in here. So there's a question here. Why only one expansion from here to here? Why? Yeah, you could not go back, right? So there's only one option. Just put the one here. Okay, okay. So on so forth. You can enumerate all of the configurations so as you can construct this kind of a tree. And then you can do breadth-first search layer by layer. Of course, you can use A star algorithm or deep first search, different search algorithms to play with the game. Okay, okay. This is the best idea. So in here is the give one more student coming in. Okay, so here's one very, very tiny exercise. Of course, we're not doing the exam. The exam, if you have exercise, there are something that you can do. That will not too complex. Too complex means that we will not give you a tree structure, include the thousands of nodes, and to ask you to find a best path. Of course, no. We will give you a total example that contain a few nodes there, and you can use different searching algorithm to find the best solution. Okay, okay. So given these 5 nodes, this is a tree. This is a graph. This is a graph. Okay, this is a graph. And the edge, the transition, we have the direction, we have the arrow. We can from right now we're starting from S and go to G. We're going to go to G. Given this connection, right now, I'm asking you to figure out a path from S to G. So what's the solution? Using breadth-first search. A quick exercise. 1 minute. Quick one. What's the solution? Using 2 lists to maintain the states and figure out which one is the best one. The starting point is S. The goal is G. So of course, we have 2 lists to maintain. One is open list, the other is closed list. We check S first. S is not our goal, so we put S into the closed list. So what are the S successors? A and B, right? A and B. So we go to A and B, put A and B into the open list, right mostly of the open list. And then we continue to check A or B. Of course, A leftmost, right? We check A. And A, what are the successors of A? Only C. because B have already there, S already there, only C, right? So we put C into the rightmost of the open list. And we continue to check B or C. Leftmost, B, right? We check B. And then what are successors of B? What are successors? Only G. And right now we go on so on and so forth. And we figure out G is here. So the path is S to B to G. Okay? Okay, just a review of the Hanson Tom. What is that? Okay, so we continue. Now we get to the second one, depth first search. So breadth first search, layer by layer. Depth search, of course, the deepest one first. And back check. Unless you could not figure out the target node and you check back, right? So this is the breadth first search, depth first search. Stack the child left to right and repeatedly go to left child, left one, left one, left one, till the deepest path, okay? Until you could not figure out the target, just go back to go to the sibling node. This is the basic idea of the depth first search. See, what's the main difference? What's the main difference? Something that is different from the breadth first search. Still, we have two lists to maintain, open list and the closed list. And we just remove leftmost set from open and check. If that is the goal, if yes, then done. If no, we just generate the successor from X, the successor. We put the successor on the left end of the open list. This is something different, left end. We check from leftmost, and we also put the new successor to leftmost of the open list. And if that have been checked, we just put it in the closed list. So the main difference is here. All right? All right? So if you look at the same problem here, from starting initial state A to some other places. If we check from A is not our goal. We just put into the closed list. So the success of A are B, C, D. We just put in the leftmost or rightmost. Leftmost, B, C, D. And we continue to check the leftmost of the open list, B. B, the successor B is EF. And we put EF into the leftmost, EF in here, right? And so on and so forth. The only difference is whenever you have a new successor, just put in the leftmost of the open list. Okay? Okay, so this is the basic idea of the depth first search. If you look at this step, you can see these paths have been checked. And the second path in here, this sort of depth first search, right? You can see a different outlook of the different algorithms in here. That's why they call the depth first search. Okay? Okay? So let's go back to this, for example. Again, we go starting from S, and right now still want to go to G. What's the solution given this depth first search? What's the solution? So what's the solution? Will it be the same with the breadth first search or different? The same or different? So we have two lists. One is open list, the other is closed list, right? We're starting from S, and we have a new successor or children node of S, A and B. And we put A and B into the leftmost open list and put A, S in here to the closed list. We check leftmost of open list A. A successor are S and B and C. S and B and C only C in here. We can put C to the leftmost of the open list, right? And put S into the closed list and continue. So on and so forth. C, we check C in here, and only G is a successor. And now we continue to check leftmost of the closed list. G is our goal, and done. Right? So the path will be S to A to C to G. You can see the solutions are different with different algorithm. So if you go back to check the algorithm, of course, there are a bunch of different papers with different metrics to evaluate. Some problem, they are doing better in breadth first search, but some problem are doing better in breadth first search. These are application wise, depends on the application itself, depends on the metrics, the problem itself. Okay, okay. And so these two different algorithms, they have their own advantages, their own disadvantages. They both can find the solution if there exists a solution. So for the depth first search, if the search space contains very deep branches without solution, one possible case if you have a tree, the tree there's a left, and here is our solution in here. You will have go to depths. You cost lots of computation or storage in here. So this is a good way using depth first search. This is probably an extreme case, right? And in here, breadth first search will be better, right? And for breadth first search, because you need to scan layer by layer, you will have to store. That is storage consumption, demanding on memory. Okay, okay. Of course, this just give you a very, very high level differences. If you're going to check the application, that if you have different application, of course, there are different advantages and disadvantages. You need to further analyze it. Okay, okay. And so far, we're talking about uninformed search. We just search based on the judgment. You have the operator, right? If you have initial state, you have the goal state. You just judge if the state is what is your goal or no. If that is yes, stop. If no, they continue to search, right? So this is uninformed search, or we call blind search, or blind search. And following, we are talking about informed search. As the name implied, we have informed search. That means we have further information. We have something. We have some information that can guide us to do the search. This is guidance. You will see what is this guidance in each particular algorithm. Okay, okay. And for the informed search, usually one will use this kind of informed search, heuristic search. One is maybe because of we don't have available data, or the problem statement is not so clear, or because of it is too computation expensive. Then heuristic may be the easy one. This is one we can use heuristic search. And usually, because we are using some information to guide us, that depends on the information you're using. If this is a bad information, probably this solution will be worse than uninformed search. So there's under the assumption that you design a very good heuristic, the information to guide you. Okay, okay. And this is the first one, hill climbing. So what is hill climbing? Climb hill. Hill climbing algorithm is a local search algorithm that moves in a direction of increasing value to find a mountain peak. You're going to go to the peak or the best solution of a problem. So imagine right now you're going to climb a hill. You're going to climb to the peak. And right now you don't have a map. Nobody tell you which path can bring to the peak. What would you do? What would you do? What would you do? If right now, imagine I could not see the road, right? I want to go to the top there. What would I do? I can only see like the radio, like around 1 meter. What can I do? I just check which direction to go, right? Just check the nearby step. If this step can bring to upper. If that is no, I just select the one that bring me to the uphill. Just local search through local search. This is the best idea of hill climbing, okay? So the information is a local search. You can compare with the local steps. This is one information you can use when you are doing search, okay? Okay, so you can, this is the best idea. The flow is that you have initial solution. I'm standing in here and I have the surrounding steps that if the step can bring me to go upper or down. This is my next solution I can check. Okay, so the best flow is that you can generate an initial solution, and which now I assume my current state is the best one. And then I see the next step and compare with my next step. If next neighbor can bring me a better solution, means that one is my current based state. Otherwise, I just stay in the same state. Okay, okay. I'll repeat until bring me to the goal. Okay, okay. So let's take a look at this pseudo very simple pseudo algorithm. The basic idea, you need to generate a neighbor, your successor, and to compare if a successor can optimize your goal, either maximize something or minimize something. We design our objective. If you're going to climb the hill, then you're going to climb the higher height, right? Right. So this is one objective you need to design first. So if you look at this, okay, so the call is here. We assume our current state is best one. And then you do the following search, how to you have a way to figure out the successor. And you compute if the successor can make your outcome better. If that's better, you just replace the current state. Make your neighbor as your current best state and do following search. This is a hill climbing. Is that clear to you? This is actual Python implementation. Doing the same thing. Is that clear to you? Is that clear to you? So, but there are some problems of using hill climbing. If you look at the state space, you're in here. You just keep climbing, right? Based on local search. No matter what, you can figure out a neighbor, a step that can optimize your objective function. This is your objective function value. Right now, you're going to maximize. You just keep climbing, right? Keep climbing step by step until here. And in here, you are nowhere to find a better one. You just stop in here. You will think this peak is your optimum solution. But practically, it is no. It's just a suboptimal one. You just stick in here. And there are other possibilities, just flat one. You just stop in this kind of flat local maximum. So this is a downside of hill climbing. You're easy to get into stuck local optimum. Okay? Okay, this is a problem of hill climbing. And the limitation is that, first of all, it could not recover from failures of its strategy and easily get stuck into local minimum or maximum. And we also get into a flat solution, right? So this is its limitation. The next one, best first search or greedy search. This is the second informed search we are going to introduce. The best first search, there's one information going to is, remember, we are talking about informed search. Usually we have some information to guide us to further search. For here climbing, that is local neighbor search and compare. For the best first search, they define an evaluation function. This evaluation function, how we spend node based on this evaluation function? It is the lowest evaluation is spent first, which is the node with the lowest one. More specifically, this heuristic function, what we use in here, it defines as the estimated cost of chips path from state at node n to a goal state. We have the current state, and we have the possible next step, right? We have several one. You can move, and right now, which one you're going to select? Which one is better? You just evaluate. If that one is bad, you can have a better way to from that one to go. This is the estimation. It's just based on the estimation of the neighbor to the goal. If the neighbor can achieve the ultimate to the goal, then you just select the neighbor. This is a best first search. So information is the function here, HN. Estimate cost of the cheapest path from state and node n to a goal state. Okay, this best first search. Okay, with these concepts, let's take a look at this actual example. We are given a map. This and each node is a city. The age, we have the cost from one city to another. Okay, so the starting point is this rod. The destination is a Bucharest. Okay, in here, Hn is the function that estimate from the state one location to a target node. That means from, for example, Arad. This is from Arad to Bucharest estimation, the cost from this city to the source destination, Bucharest. This is given. Okay, this is the Hn function. So given this map, given this matrix, right now, I'm asking you, what is the best path from the city Arad to Bucharest? This Hn here is the guidance value, guidance that to do the search. We are going to figure out the minimum cost from one city to another. This function is the cost from one city to a target city, Bucharest. But this is the estimation value. The starting point is a rod in here. So still, we start from here. This is a graph. We can directly expand the node one by one. The starting from a rod, we have how many possibilities? The successor, the children node. One possible is the ring in here and CBR. No, CPU in here. And this is Timisoara, we have 3 possibilities, but which way to go? You just select based on the estimation value from this location to the destination. Just compare with these three cities. For Zarin, 374. This costs 374. For Timisoara, 329. Sibiu, 253. Which one's better? Of course, Sibiu. We are going to minimize the cost, right? So we have 3 possible successors. In here, we just select the one with the minimum cost, Sibiu. And right now, Sibiu here, you can expand further. In here, we have 4 successors. One is Arad, the other is Oradia, and Vagaros in here, and Nicubisia. And we just select the minimum one. Which one is the minimum one? Which one is the minimum one? Huh? From Sibiu, we have the Aradia. Aradia is 380. Fagaros 176. This is the minimum one, right? We just expand from Sibiu to Fagaros. And then Fagaros, we have one successor director go to the goal, target. Let's see how get there. Starting point, Arad, we have 3 successor possibility. We just select the minimum one, Sibiu. And in Sibiu, we have 2 successors, 3 successors. And we just pick the one, which is minimum one. Fagaros, 176. And Fagaros, we have the successor, Bucharest. This is our goal. Done. But what's the problem of best first search? What's the problem with this algorithm? Huh? This is under assumption. You have a very good estimation of the current state to the target node. You are based on this information to do the selection. Okay? Okay? And there's something that easy get you start. For example, in here, the limitation. You are starting from this node. And right now, your goal node is in here. If you are select the successor based on the distance from the successor target node, you are very easy to get into the stock in here, the U-shape. Because you just search. Based on the destination from the local point to the goal. Whenever you just select the best one, you are very easy to get in here. But you found out there's a obstacle in there. You will go back from the other way. So this is one of the limitations of best first search. Okay, okay, okay. So this is the basic idea of best first search. The A-star search. You can see the previous 2 inform such algorithm. The first one just select successor based on the local information. You just compare the local neighbors, which one is the best. But for the best first search, you just select the successor based on the neighbor to the target node, the HM function. For A search, they use both. One is from the cost to reach state and from the starter. We use this as our guide information. The second component is estimated cost from end to the goal. This one component that the best first search used. This is one additional component that used by A-star. They use this information to guide the search, to select the successor. This is the basic idea. This is the basic idea. Okay, let's go use a very simple illustration. In here, we have the starting node. In here is a red one. This is a Purple one is the target node. And we are in the middle of the state. If we can go to this state, that depends on the cost from the starting node to this current state. And the current state to the goal state, the estimate cost. There are two components. Okay, the ultimate goal is to minimize the cost from initial state to the target goal. All right, all right. Let's go back to this problem. Still, in this city map, we are going to figure a way from Arad to Bucharest. And we are still given each HN. Each the estimate cost from each city to the Bucharest. And we also have the actual cost from each city to another. What will be the solution using A star search? Think about it. Just guess, think about it. You will have two information together to select the successor, to expand the node. What will be the solution? ASRV to P2B. We have one answer online. Is that correct? It's the same with yours. What will be the answer? We have to, the guidance include two components. One is to a starting point to the successor, the one particular city. And the second component is the estimated cost for a particular city to a target city. Of course, we'll get starting from the initial city. We just expand the city from its neighbor cities. From a starting point, we have three possibilities. One is Zarind, Timisoara, and Sibiu. But which one we continue to expand? Which one continues to spend? Okay, we can continue. It's the same with yours. Is the results the same with yours? A, S, R, V to P to B. The starting A, we have F, 0 plus 366. Z, that's 75 plus 374, and so on and so forth. And let's pick the one with minimum cost. What's that? What's that? Okay, so the starting point, right? We have two value. One, of course, from itself to itself is 0 cost. And from Arad to the Bucharest, that is 366. The value is in here. We have three different successors. The CPU, we have 140 from Arad to CPU, right? That's something you can check from the map. And the value CPU from CPU to the estimate cost from CPU to Bucharest, that is 253. And the second successor is Timisoara. The starting from Arad to Timisoara is 118. And the estimate cost from Timmy to Butterrest, that is 329. So on and so forth. We just pick the minimum one, CPU. All right. For CPU, we have four possibilities. Arad, Phagorus, radio, and Remicuvisia. So on and so forth. Just compute the value, figure out the minimum one. The minimum is RV. So it's the same with the ASRVPB. Is that correct? Is that correct? So this is the actual outcome, the complete outcome. From here, initial state, compare ARAD to CPU, and ARAD to CPU, CPU to RV, right? And go to P to B. That's it. So far so good for how to do a search based on HM plus FN, the two components. The starting city to the city you are compare, and the successor you're going to select the estimate cost from the city to the target city. Okay, this is how the way you expand the node to next one, so on and so forth, till to a target node. Okay, this is a star search. In here also give you some properties, of course. These are very more theoretical part. One is admissible value. So A star generates an optimum solution if Hn is admissible. And if that is, and another property is a consistent triangle property. Okay, if that is consistent, then along the way it is non-decreasing. If it is consistent, then it is admissible. These are some fundamental properties of A star. If you want to know more about this detailed analysis, you can go check the papers, A star search algorithms. You can figure out a bunch of different papers talking about A star algorithms. What we introduced today, they are pretty basic one. There are many different variations of talking breadth search, depth first search, best first search, hill climbing, and A star search. There are many different variations with different constraints and assumptions. Okay. And so for today, what we covered, they are all searching algorithms. And we cover uninformed search and informed search. The fundamental difference is uninformed search, we do not have the actual information guidance. But for informed search, we will design an estimation function to as our guidance for search. Okay. So this is the takeaway message for today. And this is our information for today. Let's take 10 minutes break and come back for tutorials. Okay.
Okay, hello everyone. So welcome to today's tutorial. Uh, it's tutorial 2, and today we will continue to this topic, search algorithm. And in previous courses, Professor Lin introduced two types of searching algorithm, informed and uninformed. And in this tutorial, uh, we will first review these algorithms and introduce a little bit more about these algorithms. And then we have several exercises, and we are going to solve these questions together. So first, we will re review these algorithms. First, it is breadth first search. The concept is we search by layers if the problem can be figured as this tree-like graph. So we search by layers, and on the on the right, it is the search graph, like from the 1, 2, 3, 4 to 10, and this is intuitive, and also this is a dynamic illustration. And for the depth first search, we search like the column wise if we use the same search graph. And this is the dynamic 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the blue numbers is the sequence of the depth first search. And so these two are quite simple, right? So any questions? I think so, no. Okay, so continue. These two are the uninformed search because we have no priors to the problems. So we just search with some strategies like the breadth first and the depth first. And the next is hill climbing. It is a heuristic search algorithm or informed. And here is a pseudocode. Like the input, it is the parameters, the maximum iterations, and the problem function f. The problem function, you can assume it as an evaluation function, evaluates how good this point it is. And the output is the current. What is current is the final answer. So we iterate the possible situations or the possible candidates among the landscape. So for each iteration, within the maximum iteration, we find a candidate from the neighbor of the current candidate and find the smallest one, smallest of f. And finally, after this loop, we return the current. So this in this pseudocode, can you answer whether we are find the maximum or the minimum? Yes, great. So we are find the maximum because this determine the f candidate if greater or equal to the f current, then we replace the current with the candidate. So we are find the maximum, right? And hill climbing is a very intuitive algorithm also because it's like us a real human in climbing, but it has some problems. Hill climbing algorithm goes uphill along the steepest possible path until cannot go further, which may return a state that is a local maximum. So here is a landscape of objective function. The axis is a state space, which corresponds to the states, all possible states, and the y is objective function. For example, this is a one state and it corresponds to one objective. And for this objective function, we can find this is the global optimum, global maximum. But there are some landscapes are difficult or challenging for the hill climbing algorithm. First is the shoulder. For example, if we use the hill climbing and we climb to here, and we find that all its neighbors are the same to this state, so we cannot escape from this shoulder. Also, for the local maximum, if we search from here, from this point, and we climb to here, and we find all its neighbors are smaller than this current state. So there is no replacement for this current state. So we are trapped in this local maximum. Also, this flat local maximum. So this is a problem of the hill climbing local optimum. And for details, there are some. So this is a summarize for these pros and cons. Pros is hill climbing can avoid traverse and achieve the purpose of improving efficiency, but the problem one is local maximum or the local minimum, the local optimum, and the Plato cases. It is also a kind of local optimum. It is the landscape shaped like this. It is a flat one. So all its neighbors are the same as this current state, so there is no replacement. Also, the ridges problem. This is a little bit different. It's like a mountain, the ridges of a mountain, and you just shift between points, but you cannot escape this regions, and so the climber or the algorithm can only ascend the ridge by zigzagging. So these are three problems of the hill climbing algorithms. So any questions? Okay, no questions. So we will have several exercise. The first one or the first two one are very simple. It is a warm up. The first is given the problem solution graph in figure 1, perform a breadth first search starting from the initial state A and ending in the goal state F. And if there are two or more nodes of the same preference, then handle the nodes alphabetically. This means, for example, for the A state, it has three neighbors, B, C, D. And the first one you need to visit is the B, because here we follow the alphabetical preference. So 2 points, 2 key points, breadth first and alphabetically. So draw the search graph, and we can have 2 minutes or 1 minute to solve this problem. It is quite simple, right? You can have a try. Okay, let's check the answer together. So starting from A, and it has three neighbors, B, C, D, and since alphabetically, so we first visit B, then C, then D. And for the B, there are no neighbors that haven't been visited because B has two neighbors, CD, but has been visited. So we continue to C. And for the C, it has only one neighbors, E. So C for E and D for F. So this is the results for the breadth first search. A, B, C, D, F. A, B, C, D. So there is one more. So E, the A, B, C, D, E, F. The correct answer should be A, B, C, D, E, F. And the second exercise is given the problem solution is the same as the figure one, perform the depth first search from the A to F. So the initial state and the final goal states are the same. But here we perform the descending alphabetical order, which means for the A, it has three neighbors, B, C, D. You should first visit D first. So maybe we can also have 1 minute to solve these questions. Okay, this is also simple, right? So we check the answer. The answer is A, D, F, just the right line because the problem asks us to starting from A to F. So first we starting from A, and it has three neighbors B, C, D. And since we visit in descending alphabetical order, so the first we need to order is the D. And since we perform depth first, so next we start from the D. And we find the D has two neighbors, E and F. And F is descending compared to the E. So we visit F and we find the goal state. So this is ADF, the answer for this problem. And for the black dots and the dotted black lines and the dotted lines is the whole search graph, like ADF. Then we find the F for F. There are no neighbors, so we backward to D, and we find D has one another neighbors E. So we continue to E. Then when we arrive at E, we find E have two neighbors, F and B. And F has been visited, so we visit B. And when we arrive B, we find B has also two neighbors, the D and the C. And the D also has been visited, so we visit C. So the right lines denotes the answer to this exercise. And the right lines with the black lines denotes the whole search graph for this problem. And the dotted line is not the search problem, but just an indication. So here we also have one answer, ADF, that's correct. So any questions for these two exercise? Mm-hmm. So for this exercise too, the algorithm will end stop at F. Yes. So any more questions? No, you don't need to. You just draw the ADF. That's enough. Okay, this is just a warm up. Now we have a little bit complicated question. So here is exercise 3. The exercise 3 is in the chess problem, but is a simplified chess problem. The four queens problem, and I think some of you may heard about this problem. The queens in the chess problem, it can attack in row, in column, also in diagonal. So the four queen problem consists of a 4x4 chessboard with four queens, and the goal is to place the four queens on the chessboard such that no two queens can attack each other. Each queen attacks anything in the same row, in the same column, or in the same diagonal. So, for example, this is an answer for this four queens problem because we find each pair, any pairs of queens do not attack each other. So this is an answer. But now here we need to design an algorithm and perform the algorithm to find all the answers. And here we define some key notations. Like first, state. State means a search state, and a state contains four queens on the board, and one queen per column from x0 to x3, and variables x0 to x3. And where xi is the row position of the queen in the column I, assumes that there is one queen per column. And the domain for each variable also is 0 to 3. And the initial state is a random state. So you can initial x0 to x3 with the random variable, with the random numbers within 0 to 3. And the goal state is four queens on the board, and no pairs of queens are attacking each other. And the generation of a solution is you swap the row position of two queens, and the objective function is the number of pairs of queens attack each other directly or indirectly. Here is then the problem is can you perform the hill climbing or any other search algorithm to find the answers of the four queens problem? Start from the initial state to the goal state. We will have maybe you can first understand this question. Just understand it. You don't need to solve it. Just understand these questions. And any questions about this question, about this exercise? Okay, if no questions, we can show you some ideas about solving these problems. For example, we start with the initial state for x0 to 3. And we can see if x0 is 3, we place a queen here, and x1 to 1, and we place a queen here, and x2 to 2, we place a queen here, and similarly x3 equals 0, we place a queen here. And here is one state, or the initial state. It is random. And the way for generating a new solution is to swap the row position of two queens. For example, if we swap x1 and x3, the next stage of swapped result should be in x1 the queen is here, and in the x3 the queen is here, right? So this is how we generate a new solution. And if multiple solutions have the same objective value, select the solution where the pair of queen swap has the smallest subscript or column number. This means if, for example, when we can swap either x0, x1, or x2, x3, we will swap x1, x0, x1. When we can swap either x2, x3, or x1, x3, we will swap x1, x3 because the sum of the subscripts are the smallest. So any questions so far? for the random generating the solution and the swap strategy. Okay, if no question, we show the first step. The first step is um, in the initial stage, as just mentioned, we initial as the 3120, and this is the initial state. The first is we need to calculate the cost. The cost is 2 because there are two queens attacking each other. This one and this one and this one and this one. So the x0 attack x3 and the x1 attack x2. So the cost is 2. And our goal is to find a state that cost is 0, right? And this is its neighbors of this state. For example, we swap x0 and x1. We swap is like between 3 and 1. And here is a found state like a 1, 3, 2, 0. And since column 0 and column 1 has been swapped, so this is the state and the cost is 1 because only one pair of queens attacking each other. So the question is start from this initial state and search by this swapping strategy. This is the swapping strategy like first we swap 0, 1 and 0, 2, 0, 3 because the sum of subscripts are smaller and find the final answer. And now you can try to answer this problem. This is a little bit complicated, so we can have 3 minutes to solve this page, just only this page. You just need to calculate all the costs of the following 5 states. Okay, let's check the answer. These are just some calculations, right? You just enumerate all the states and calculate the cost. Here, I just take one as an example, the third one. If we swap the x0 and x3, x0 and x3, and we obtain the result as 0, 1, 2, 3, here 0, 1, 2, 3, and the cost should be 6, because although we only have 4 coins, but the pairs are 6 pairs, right? Because here, for example, uh, 0 and 1, 0 and 2, 0 and 3, and 1 and 2, 1 and 3, and 2 and 3. So we have 6 pairs of queens attacking each other. So this is the cost of its neighbors. And the next, what should we do? Remember the hill climbing for the current state, and we list all the neighbors and calculate the function or the evaluation function for the all neighbors. Then we select one neighbor to replace the current state that the neighbor should be better. And here we want to find the smaller cost or the zero cost. So we need to find a state that has cost smaller than 2. And since uh, here we select the smallest subscript, so we find that the first one within the cost is 1. This, and this, and this 4. We select the first as the next neighbor. So the next neighbor should be, next state should be 1, 3, 2, 0. And the next is again, we need to list all the neighbors of this second state and calculate the cost and perform the iteration. So again, we also have, maybe we can also have 3 minutes or 4 minutes to answer this exercise. And this time, you should complete the exercise, which means you need to find the final state. Let's check the answer. So the answer should be the cost corresponding. And for example, the third neighbors, and we swap x0 and x3, obtain this state, and we found the cost should be 4 because uh, 0 and 3 is one pair, and 2 and 3, and 2 and, 0 and 2, and 1 and 2, and 1 and 3, and 2 and 3. So we have 4 pairs. And luckily, we find that the 6 neighbors, like we swap x2 and x3, obtain the answer for this problem. Uh, so any questions for this exercise? Okay, if you have no questions, so I have one question. Is the algorithm we use to find the 4 queens problem the same as this hill climbing algorithm? Are these two the same? The idea are the same, but are they exactly the same with this pseudocode? Pardon? Uh, so you mean uh here we need to find the maximum, right? And in the 4 queens we find the, yeah, this is one difference. Any other difference? Let's see the online. How do we know? First, get rid of any setup where 2 or more pieces are in the same column, leaving just 250. If 2 or more pieces attack each other, stopping check that arrangement and move on. Okay, this is one kind of algorithm design. So how do we know which tools to swap? Okay, so this is also the question that I want to mention. In this pseudocode, we use the random neighbor, but in our 4 queens, we enumerate all neighbors. This is the difference. And to answer this problem, how do we know which to swap? We enumerate all neighbors. So we enumerate all kinds of swap strategy from the swap x0 to x1, from this one to the swap x2 and x3. So we enumerate all the neighbors and find the minimum or the according to this ordering strategy, find the smallest subscripts. So this is the key difference because in this uh, in these 4 queen problems, the neighbors, the search space is quite small. So for each initial state, we can enumerate all its neighbors, and we find the smallest one. This is a kind of like the breadth first, but in this pseudocode, uh, we just random guess one neighbors and compare this candidate and replace it or not. This is kind of like the depth first. So these are the two key differences. And this is the exercise 3. And finally, we continue to exercise 4. This is the final question for today's tutorial, but it is really complicated. And this question will examine the A-star algorithm. And the question is perform the A-star algorithm on the following graph and explicitly write down the query at each step, while the red figure means the heuristic value, like for the 14, 10, 4, and the black figure is the path cost. For example, from S to A, the cost is 6. From S to B, the cost is 5. And for example, from F to G, the cost is 3. And the red figures are the heuristic value. For example, if we are in the S state, the heuristic value should be 17. And if we are in the F, the heuristic value should be 1. And the problem is write down the query at each step, like maybe, for example, the search should be S, A, E, F, G, or anything else. And you can try to solve it. But first, any question to this question itself? So you need to make sure you understand this question. Okay, if no questions, okay, let's see. Any questions online? Oh, it's like a factorial again. Yes, you can say it is a factorial. Oh, it's a mathematical. Okay, so I will first present one example as the state, from S. The left side is the pseudocode. You can refer to this pseudocode, or you can just use your understanding for the A-star algorithm. And so in the initial stage, iteration 0, and the open list should S because we start from S, and the actual cost G is 0 because we haven't gone any. We haven't visited any stage, and the heuristic value H is 17, and so the F should be G plus H, so also 17. So the example is if we from S, it has 3 neighbors A, B, C. So we explore S and place its neighbors A, B, C into the open list and place S into the closed list. The closed list denotes that we have visited. And so the sequence is S because from the S. And so for S, it's 3 neighbors A, B, C. And for the A, the cost is 6 because from S to A it is 6. And the heuristic value for A is 10. So the F, the H plus G is 16. And for the B, also 5 plus 13 and 3. And for C, 10 plus 4. Because from S to C, the cost is 10. And heuristic value is 4. So it is 10 plus 4 for the 14. So you can try to complete this stage. Maybe you can just try to complete one next stage. So which is the next stage that we need to visit? Yeah, that's correct. And for the C, what are the neighbors of C? Yeah, that's correct. The D. And so what's the F value for the D? The F should be G plus H. So you need to calculate the D, calculate the cost of D and the plus heuristic value of D, the two. And you can try to solve the next stage. Maybe we can have 2 minutes. Okay, let's check the answer together. So the next iteration should be 2, and as you just mentioned, what we need to visit is C, and the neighbor of C is D. So we take C out. We visit C. The current state is C, and the open list now is ABD. Because ABD we haven't visited, and we put C into the closed list because C and S has been visited. So after iteration 2, within ABD, what should we visit? The answer is here. We need to visit A because in the ABD, within this open list, the A is 16 and the B is 18. And for the D is the cost is 10 plus 6. It is 16. And the plus is heuristic value 2. It is also 18. So within ABD, within this open list, the smallest one is A. So we visit A and we find the neighbor of A is E. And we calculate the F value of E. The um, G value is 6 plus 6. And the heuristic value is 4. So it is 6 plus 6 plus 4. It is 16. So now we arrive iteration 3 and we have open list EBD and the current state is A and the closed list is SAA. So what should we visit next? So what should we visit next? The E. Yes, we need to visit E. So what are the neighbors of E? The B and F, right? So, but B is also in the open list. So what should we do? So maybe you can spend 1 or 2 minutes to think about the iteration 4. It is a little bit different compared to previous steps. Okay, so let's check together. So within this open list, okay, pick E. Yes, pick E. And so we pick E and find E has 2 neighbors, B and F. And so 2 neighbors of E, B and F. But this B is different from this B because this B has a very long cost. It should accumulate from S, A, E to B. So it is 6 plus 6 plus 6, it is 18. Its cost is 18. And its heuristic value is 13. So the F value of B, it is 31. So this B is larger. Its F value is larger than this B. So we would not uh, place this B into the open list or replace this B. So this B remains and this B will be ignored. And the F for the F, its cost value is 6 plus 6 plus 4 and is 16 and heuristic value is 1. So it is 17. And so we only place F into the open list and take the E out into the closed list, and the current state is E, and the current open list is BDF. So what should we choose next within the BDF? Yes, the F. So next, we choose take F out. And we take F out, we also find that F has two neighbors, the D and the G. And we take the D out and calculate its cost 6646 22, and its cost, its heuristic value is 2, and its F value is 24. And here we also find that G is out. We may find G. The G is 19. The cost value is 6641. And sorry, it's 6643. And the cost value is 19. And it has no heuristic value, so it's 0. And the F value is 19. So we take F as the current state, also put F into the closed list, and now we have open list B, G, D. So what's the next step? So what should we pick next? Uh, m- Maybe you can think about it. Should we pick G? No, we shouldn't pick G because G has a F value 19 greater than B and D. So we need to pick B or D. Let's see. Yeah, we pick B. So the next, in fact, we pick D. So the problem is, okay, also. So, uh, the open list now is BDG, and in fact, here we can see in fact here you can either choose B or choose D because they have the same value, and according to the pseudocode, you just choose the minimum, and if the minimum are more than 1, you can just pick B or D. And here we choose D because uh, we want to illustrate more. Because if we choose B, we will arrive at the answer. So if we choose D, and we take the D out as the current state, and we find it has two neighbors, B and F. This is also one more situation, because we find that the neighbors of D, B and F are either in the open list or either in the closed list. This is also a different situation compared to the previous steps. So if we choose D, so we find its neighbors B and F, and we calculate the F value of the B, and it is 36, and for the F it is 23. So for the D, its all neighbors are not acceptable. So for this D, we in fact we only perform take D out into the closed list, and we add nothing into the open list. So this is quite different from the previous steps. So finally we arrive 6. We have B and G, and now compared to the B and G, again we will choose B rather than G because f of B is smaller than G. So if we choose the B and we find its neighbors are the E and D, and we calculate the value of the E and D. For the D, the cos is 5 plus 6, 5 plus 7 and is 12, and the heuristic value is 2. And for the E, it is 15, and for the D is 14. So here is also a different situation. We find the D and the E of the neighbor B, and we find that in the closed list, D and E has been in the closed list. I just mentioned the closed list denotes the nodes that we have visited. But can we modify the closed list, or is this fixed? The answer is no. If the closed list is fixed, we do not need to maintain this list, right? Because it is also dynamic. So even the D and E is in the closed list or are in the closed list, we need to compare them because according to the pseudocode, for example, neighbor in closed list F greater than the neighbor of F will also perform the replacement. Like we will check the the D, the neighbor of the B is D and E, and the closed list also contains the D. For example, we take the D. The D in the closed list, if you remember, where do we find it? We find it by the path SCD, right? And its F value is 18. So the D here in the closed list 1 has a value of 18. But if we search from SB to D, its F value is 14. It is smaller than the D here. So we will take the D out of the closed list and add it into the open list. And this is similar to the E. If you remember, where do we find the E? We find E here. Follow the path SAE. And if we roll back, the F value of E is 16. So, but here the F value of this new E is 15. So both E and D will be deleted from the closed list and added into the open list. So maybe now you may think we find more states in the open list, and now you have GDE. The next, what should we visit? Yes, the next we should visit the D. And for the D, its neighbors are the C and F. And also, you have encountered this situation, right? Because you have encountered that the neighbors that are in the closed list. So the neighbor in the closed list C and F, you should compare it. But here is different. In the previous, the D and the E are both replaced, take out from the closed list. But for here, if you follow SBDC, you find this C is greater than this C, so you will not take out C out from the closed list as into the open list. You will not visit this C. But for another neighbors of the D, the F, you will add it into the will you add into the open list? So you need to also roll back to find whether this F is greater than this one. So you roll back, find this F is 17. And you find this F is 19. So you will not add this F. So this SF, although they are in the closed list, they will not add into the open list. So the current state is G and E. So what's the next? is E, right? So E is smaller. And for the E, we find its neighbors are A and F. And we find A is greater than this A. So we will not add it into the closed list. But we will add this F because before this F, its value is 17, but this F is 16. It is smaller. So we'll take this F out of closed list and add into the open list. And the currently one is G and F. And again, the same. We visit F, and we find F with its neighbors and D and G, and D is greater than the previous D, so we will not visit D. And finally, we find the G. The G, this G has the cost of value with 18, and F value is 18, and this is smaller than this G. So finally, we take this G out. So the sequence or the query of the state is S A A E F D B D E F. So any questions for this exercise? Okay, if you have no question, I have one question. Is this sequence the only one sequence in this exercise? Is this one the only one? Remember this state? The iteration at 5 with the current state F and the open list BDG, you can visit either B or D. And in this exercise, we didn't set whether you should visit alphabetically or ascending or descending. So you can choose B or D. So if you choose B, the next should the B. If you choose D, it's this answer. If you choose B, it is another answer. So this is not the only one. And thanks for your time. Then today's tutorial will end.